Okay, so now what we will do is that we will explore the modeling of the BJT, first starting with DC model and then go into AC model for doing your small signal analysis. As you have seen from that graph over there, you can do small signal analysis, AC analysis, graphically also. If you know all these characteristics in detail, you can use a graphical system also to determine with AC analysis. So you can get everything from this graph if you know these characteristic curves exactly. But the easier way is to use a model to do your small signal analysis of the amplifier. Okay? As you can see, the model, by model I mean the operation, the behavior of the BJT at this point. When I say model, that means what is the behavior here? When I say the model, a model is at a certain operating point. So the model of the transistor, what is the model of the transistor here? That will be a DC model. Then you would say, what would be the AC model? That means, if you are here and you change your currents, disturb your circuit, then what is the variations in collector current, collector emitter voltage? That is your AC model. Okay? So you model your transistor at the operating point, and then you see what happens when you vary the operation of the circuit across the operating point, across the set operating point. So you see here, if you move, this is a very small distance from the operating point. So you are trying to develop a linear model. That means everything is linear. If you add something certain amount, then the other quantity will also increase in the same proportion as you increase the original quantity. So it will be linear. So across the original operating point, you expect a linear behavior. So you're trying to develop a linear model, straight line model. That means like a resistance, a straight line. If you apply a certain voltage, it will give you a certain current. It is not non-linear, it is a linear operation. That linear behavior will only be valid for a small variation across the operating point. So if you vary your signals, small signals across the operating point, that will be linear variation, and your analysis will be correct. But if you vary too much, you see from here, if you go here or here, it is going to work because you have left the linear region. You have moved here, non-linear region. See, if you go from here to here, no problem. If you go from here to here, you go into saturation, which is, as far as the gain is concerned, a non-linear region. So only a linear small signal operation is valid in close proximity to the operating point. So that's what you're trying to do here. Okay. So all of these things you know now, so I don't have to occupy the board with these quantities anymore, which you have already grasped reasonably well. So I'm going to erase all of these things here, because I have to develop the model. So you can see here, when you operate this BJT in the forward active region, this between base and emitter works like a what? This junction works like what? Base and emitter?
Forward bias diode.
Forward bias diode, very good. So we can start a DC model by drawing a forward bias diode between the base and the emitter. So your base is a P and the emitter is a N. So you have a PN junction. So this is your base, this is the emitter. Okay? So you got half of your model. So this is your DC model. DC BJT model. Okay? Then what happens between collector and emitter? You can see that between the collector and emitter, as you change your collector emitter voltage, you see here, as you change your collector emitter voltage, does your collector current change? This in the linear region, as you change your collector emitter voltage, does your collector current change?
Yes.
Does it change? How much?
Very small amount as you go through.
Small, isn't it? So as you go, you look at the curve. So as you go from here, it's just a small chip. So approximately, it doesn't change, isn't it? So as you change your collector emitter voltage, your collector current doesn't change. So if you consider a situation or a device where, or a branch, okay, where as you change your collector emitter voltage, the current between the collector emitter doesn't change. The current between the collector emitter doesn't change as you change the voltage. So what kind of component is that? When you change the voltage, but the current is fixed, what kind of component is that? Current source, exactly. So the output behavior of the BJT is like a current source. So we can put a current source here. This is emitter, this is collector, and this is your current source current IC. Okay? As you change your VCE, it doesn't change. And what is the relation between this collector current and the base current?
Beta.
Beta, very good. So this is your beta DC. Okay? This is the IB. This is IC, this is the collector's emitter. Or this is a large signal model, isn't it? So you can show it with DC like this, or you can show with the composite also like this. Small I, big C equal to beta DC into small I, big B. So this is large signal, this is a large signal. This is large signal, this is large signal. Okay, the entire signal. And you can say here this is small I, big B. Okay, and this is an emitter. This is your base. This is your collector. So this is your DC model. Okay, it's very simple, isn't it? Everybody agree? Everybody agree that this is a suitable DC model? Okay. So our main goal is to do small signal analysis. So we need to know what is the small signal model. Okay. For the small signal model, we can exactly go from here and change all the currents, you know. Okay. So small signal model, you can start from here. You can have, again, you put a box here. That means there's something here. You know. And then small signal also, we can have a current source here. Because why we have a current source? Because we are saying that this part is linear. That means for a given change, if you change the base current from here to here, the collector current, okay, base current from this value to this value, the collector current changes from here to here. If you change the base current from here to here, the collector current changes from here to here. And those ratios of change are exactly same as the DC. So we say that beta DC equal to beta AC. That means for a change in collector current, that means delta IC by delta IB equal to beta AC, which is equal to exactly IC by IB equal to beta DC. Okay. The small change in the collector current ratio with the small change in the base current, which we call beta AC, is possibly equal to the large signal IC divided by large signal IB. Okay. In that case, we can also put a current source here for the AC model. put a current source here. So I'll use, instead of using large B, we'll use small. That means it's a small signal. Put a P here, put a small c here, put a small e here. And you have here, this is your small I, small c, small signal. Just the change, which is equal to small I, small c is equal to delta IC. The change in the composite signal. And this small I, small c equal to what? How does it relate to IB? So IB is going here. IB is going here. And this between here and here is what? Between base emitter, what do you have? It will be a resistance. So it's actually a voltage between here and here, VBE between here and here, and there will be resistance here. Okay? And you have a collector current here. What is the relation of between this collector current and this base current? You can also write like this way. You can also write this as small I, small c divided by small I, small b equal to beta AC. So what is the relation with the IB here? Small signal current IB?
Beta AC.
Beta AC. Beta AC into small I, small b. Okay. So here now, instead of a diode, the diode shows you the exact drop between the base and emitter. Okay, and here you show only the variation of the drop. So which is really like a variation of IB with VBE. Okay, VBE divided by IB. This variation of VBE with IB is in this box. The question is, how do you find it out? How do you find it out? So this one is more or less done, IC, beta IC, AB. But this one, how to find it?
Could you repeat that, please? Sorry. Could you repeat that? Sorry.
This resistor, because I'm saying that you have a VB here and IB flowing through here. So ratio between VB and IB is a resistance R. And what is this thing? What is the value of this thing? So that you can put it here and complete our AC model. This one we can see we have got beta AC into IB. Beta you can get from the chart, from the graph, or it can be given by the manufacturer. We can put it here and we get IC. But what is this? How do you get this? This is not given by the manufacturer. How do you get it? That's the next question. How do you get it? If we get it, we put this here, we finish the first part of the AC model. Any idea how we can, what can we do? What will you do? Usually what do you do when you get into trouble? What should I do? Okay, let's think simple, So VB by IB, we need this resistance R, whatever you call it, equal to VBE by IB. Okay? This now you can write this equal to 1 divided by IB divided by VB. There's a little bit of calculus here. Is it correct?
Yeah.
Rangi, is this correct?
Yeah, sure.
Okay. So now what can you do is that we look at this thing now. We look at IB by VB. So we just erase this thing here now and we'll do that here. IB divided by VB, this is all small signal, equal to IB is what? IB is delta IB. The change in the composite signal, composite base current. And what is VB? The change delta in the composite base emitter voltage. Okay, and then we can always change the delta into D, differentiation calculus. Okay, so we can again do this equal to D IB divided by D dB. Okay, and what is IB? Remember IB? IB equal to the composite base current, which is a diode, equal to I sat saturation e to the power small v big B by Vt minus 1. This is equation of the diode for the composite base emitter voltage small v big B. Okay, so if you differentiate this with respect to Vb is how much? So D IB divided by D VBE is equal to IS will stay here, 1 upon Vt will come here, and then this one will go away. You will have e to the power small VBE by Vt. But you can say that this IB is also approximately equal to IS e to the power VBE by Vt. Neglect the 1, which is very small. Okay, this will be quite large compared to 1, so you can approximately neglect the 1 and say IB equal to this. If you do that, then this is equal to small I big B divided by Vt. Can you see? Can see now. This place over there, your original place where you used to sit. Is there for you? Can you see? I don't think it's a concern. Can you see? Yes. Do you understand what I'm doing? It's different, it's basic calculus, high school calculus. Nothing more, nothing complicated. We have to do a little bit of math, which we can't really ignore. We want to throw away all the math, but unfortunately, some of it will come back always. Okay. So, are you all with me up to here? Then I'll go to the next step. Are you here with me? So, here we said that we wanted to find what this resistance is, which is the relation between VB by IB flowing here. Okay. Then from this I wrote like this, and from here I went here. And I am saying that as per our discussion in the previous hour, IB is delta small I big B, VB is delta small v big B, and the delta you have always known in maths, first year, second year, high school, can always be incremental because you are talking about small distance, small gaps. So for that, delta can be just differential distance dIB, differential current dIB, differential base emitter voltage dVE. So as soon as you go to D, then you can put IB here and then do differentiation, calculus. IB equal to this, okay. IB equal to this, then dIB that dVB is equal to this just by differential calculus, and then I am saying that IB also can be said approximately equal to this. Then we put this IB here and VT here. So that is your dIB by dVE. Okay. So take your IB and VT and put it here now. So this is equal to your 1 divided by small I big B by VT. Just take here, take this thing and put it here. Okay, you with me, Ishka? You can follow? So what can we do this here? So we can put the VT on top. We can put here equal to VT on top, and the bottom we have small I. We have small I, big B. So can we make the small I, big B into just the large I, big B? Okay, if you do this, you can see here this is equal to VT divided by large IB. This is small I, big B, which is equal to large I, large B plus small I, small b. Right? We can write it like this: small I, big B, the composite base current, equals the DC base current plus the small variation in the base current. Now, can we neglect this here? Is this too large compared to this? Can we just neglect this? This IB is large compared to this small I, small b. So, can we neglect this?
Yep.
If we neglect this, then this is approximately equal to VT by IB, which are all known. So, once you bias your circuit, you know what the IB is, which is IBQ. VT is 25 millivolts at room temperature. Then you know your R pi. Now you know the value of this, which is actually called R pi. So R pi equal to VT by IB. Why is it called pi? People say this is called, it looks like a pi, you know, I don't know. So this is called a pi model. Pi model. Okay, so this is called pi model. So then we clean it all up. Our pi model consists of a resistance, AC model, current source. Okay, this is your R pi, and R pi equal to what? R pi equal to VT divided by I. This is R pi. Okay, and this is your base, this is your emitter, this is your collector, and this is your RC equal to beta AC into IB. So this is your complete model where everything is known. So once you bias your circuit, you know what is IB, you know R pi. So your small signal model at the operating point is known. And you can take this and plug it here and get your small signal analysis without going to the graph. Okay. Okay. Now I'm going to, I need a little bit more space. I don't want to erase all of this. Maybe I'll erase something here. I'll erase this. Can I erase this? Can I erase this? I'll erase this. We'll draw it again on Monday, you know, when you start doing AC analysis. So you take this, so we have developed this pi model, which is this, we take it here. R pi, this is base, this is IB going this way, this is emitter, this is IC equal to beta AC into IB. Okay. Now we want to do a bit more. We want to express, we can express the IC in terms of IB. We can also express the IC in terms of VB. How is that? Okay, let's start. So IC, small I, small c equal to beta AC into small I, small b, which is again equal to beta AC into But we know from here, small VBE divided by IB equal to R pi. Okay? So IB equal to VBE divided by R pi. So this is equal to beta AC into VBE divided by R pi. So now we got IC in terms of VBE. Okay, then we go dig little deeper. Beta AC into VBE, you leave VBE here, there's not much you can do with it. R pi, you take that R pi here, VT by IB. VT by IB. And again, this is equal to VBE divided by VT divided by IB, and the beta AC you can bring here, or to make it look easier, what we will do is that we won't do this, we will bring the IB on the top here. So it will be IB beta AC into IB into VBE divided by VT. This IB will go here, VBE by VT. But this beta AC is almost equal to beta DC, as we said. We have declared here beta AC, beta DC acceptably close. So we can say this is equal to IC, large signal IC, into VBE divided by VT. And this equal to, we call a quantity GM, transconductance, into VBE. Okay? Well, GM equal to IC by VT. Okay? Take this together.
What does GM stand for?
I'm writing down. GM stands for transconductance. So you can write IC equal to GM into VBE. So this is the complete pi model where you have the collector current represented in terms of base current, collector current represented in terms of base emitter voltage, small signals. Why is it called transconductance? Can you tell me? Why is this called transconductance? GM into VBE. IC equal to GM into VBE. Why is it called transconductance? Why is this quantity IC by VT called transconductance? Anybody? Why would you call it? Conductance means there's a relation between current and voltage. So it makes sense. There's a relation between current and voltage. The current is here, the voltage is here. Conductance is a relation between, like a resistance. Resistance is a relation between voltage and current. Conductance is the opposite of resistance. Also relation between voltage and current. So GM VBU, IC equal to GM VBE is a relation between a current IC and a voltage VBE. Current is here and VB is here. So why is it called trans? Why don't you call just conductance instead of transconductance?
There's a conductance at another spot.
Exactly, brilliant. The conductance is another spot. Or you have a your voltage is here in this branch, and your current is not the same branch. Your current is here. That's why you call it trans. Like transfer, we transfer you to Palmerston North, then you will become a trans whatever trans student. You don't want to go there, isn't it?
I'll stay here by that.
But sometimes we have to say trans because it's between two different branches. That's why it's called transquantum. So this one is a nice model. This is a nice model, pi model. Okay, this is the pi model. This is pi model. For some reason, the pi model is not the nicest model. We can make it nicer, more beautiful. Okay, how? How much time I have? Okay, I think we have 50 minutes is enough. So this pi model, it looks nice. It's very nice. You have got this resistance value, you know, this GM, you know all the expressions. So once you know the DC collector current, you know what is the GM, because this is fixed. This is fixed. Once you know the bias point, you know the GM, you know the R. Okay. So we want to derive another model, which looks even better, which is more simpler to use. So for that, I have to erase some more board. So where should I erase? Have you understood any questions here? You have to tell me now. Any questions here? Any questions here? Raise your hand. Anybody who is totally lost, raise your hand. Absolutely lost. You don't know where I am. Okay, you come here. So you tell me, how are you lost? Where? Lost in the pie.
Yeah.
Yeah, where?
So like, I get this.
Yeah, this is the alpha is this voltage.
Yeah.
And then we have to derive it, you see.
Yeah.
So we derived it this way, this way, this way, going here, this way, this way, this way. We derived it.
Yeah.
Okay, then this is the R pi you get from VT by IB. Okay, so that's the pi modeling. And then we were not happy with just with R pi. So here what we did is that we derived the current, collector current in terms of base emitter voltage. Before we just had in terms of IB, we derived it in terms of VT by creating a new term which is called GM. And which is from here. From that we got IC equal to beta AC into IB, and then we played around a little bit. Beta AC is here, and IB from here you can see VB by IB is R pi, VB by IB is R pi. So the IB must be equal to, take the R pi downstairs, then this is your IB. Then take this and put it here.
Yeah.
Okay, replace this with this, and then put the value of R pi here, which is here. Okay, put the value of R pi here, and then take IB to the upper side, okay, in the numerator, and then beta AC into IB is one quantity, and VB by VT is another quantity here. So these two together, beta AC into IB is your collector current. Okay, so you put the collector current here, VT remains here. So IC by VT we call GM. So you have now converted IC in terms of IB to in terms of VB, and you have written down here. Are you happier now?
Yes.
He's happier. Anybody else? Yeah.
Which one's the pi?
This is the pi. This is the pi. It doesn't look like a pi,
I thought they were all A's.
It looks like it's a probably inverted pi. The pi is like this, isn't it? Pi is like this, isn't it? So this is the inverted pi. I don't know why they call it pi.
Wait, so it's not even mathematical pi. So.
No, it doesn't look like mathematical pi, but this is what they call it. I would like to call it something else, but I will be differentiating with the textbooks. We don't want to do that. So a pi, what reason it is called a pi, we don't know. Something is sometimes called, like you name your cat for some reason, isn't it? Why you call your cat Jim, Tom, whatever, nobody knows. Same like that. You call something, give something a name. It doesn't have to exactly be like that.
What is that?
But you don't use it times.
Does GM have a unit?
Very good question. Does GM have a unit? That's an excellent question. Does GM have a unit? You tell me. This is current, this is voltage.
That's ampere volt.
GM is ampere per volt. Ampere per volt with R pi is volt by ampere, which is ohm. Ohm is it's a reverse of this ampere per volt. This is ohm, and this can be called mho. Mho. Sorry. MHO, mho. So ohm, you take your ohm, convert into mho. Or you take your omega, convert invert into omega, then this is that. It's not a joke, it's true. Yeah. So this is your inverted omega, this is actual omega, this is ohm, this is mho.
Oh, that just turned me upside down.
Mho. MHO, mho.
Can we just write O and then to the power of 1?
Yeah, you can use this. You can use this for ohm. You can use this for mho. Conductor. This is for resistor. This is for conductor. No, this is the real world.
What happens if your circuit's upside down
Huh?
and you read your circuit upside down and then you just think everything's the opposite of what it is?
Kill him out.
Then what do you do?
You just
No, the pi is always going to be like this. You don't upside down this one. This one is going like that. You can slide it like this, that is, but this is going to be it. And resistance is always going to be resistance. Conductance is always going to be conductance. Okay. So I have another 7 minutes that I probably won't be able to complete another model, which is a variation from this model. From the pi model, I want to go to another model, which is called a T model. T model. T. Like your breakfast, pi and T, right? So I'm going to erase one. So everybody clear of this? So I'm going to erase this part now. Still keep this R pi equal to Vt by Ib and Gm equal to Ic by Vt, and this is your ohm and this is your mho. So that model, pi model, I want to convert it now into a T model. How do I do it? So I have to do a little bit of trick. This is your base, this is emitter, this is R pi, okay? And this is your collector, this is your IC, this is equal to beta IB equal to GMVB. Now look at the R pi, R pi, so you have to see here, this, what is the relation of R pi with GM and beta? Okay. What is the relation of R pi with beta and GM? Because we have beta, we have GM, and we have R pi. So that you can deduce in many ways. One of the ways you can see here, beta IB, okay, beta IB equals GMVB, GMVBE. Okay. So R pi equal to VBE by IB. So from here, what is VB by IB? VBE by IB is equal to what? Beta by GM. So this is equal to beta by GM. So you can write R pi, or you can write beta by GM. So what I'm going to do is that this current source here, I'm going to take this current source, disconnect from here, okay, disconnect this current source from here, okay, and I'm going to supply this current source into the base, IC, and then from the base I'll take it away, put it back here, IC, which is equal to beta IB equal to GMVB equal to beta IB equal to GMVB. Okay, so this is your base current IB, and this is the emitter current. You can actually combine them together and can go one step down, and this is the emitter current I. This is the emitter. This is your collector current. Okay. So what I'm doing is that I'm taking this current source, putting this current to the base, and again taking it away. Did I disturb anything? Take the current source, give it here, and take it away. Does it change anything? The Kirchhoff current law doesn't change here, because if you take the sum of the currents here, this current plus this current plus this current minus this current, so you get this current plus this current. If you look the sum of the currents here, this current plus this current equals this current. See here, this current, base current plus collector current is the emitter current. This is IE. Look here, this current plus this current equal to IE. So your current doesn't change here. Your current doesn't change here also, because at this load you are giving this current and taking it away. If you give and take it away, is there any difference? Is there any difference? If you give, it's like you deposit $100 in your bank, and after 1 hour you remove your money from your bank. So you still have the same balance. That's like accounting. Okay? So here you can see, if you apply this current, taking it away, then it doesn't make any difference. Now I have to simplify this further to produce the T model, and I'll need another 5 minutes. Do you want to stay, or you want to do it Monday morning?
Monday morning, I reckon.
Monday.
Yeah, I think it's.
Yeah.
Okay, so we will complete the T model on Monday morning, and then we'll do small